So molecular geometry is going to look specifically at a three-dimensional arrangement of an atom, of its electrons, of everything that goes into that molecule in space. So now we're going to take those two-dimensional pictures that we drew, and we're going to be able to draw them and look at them and shape them and view them into 3 dimensions. Okay? So we're going to look at the number and the type of what we consider to be electron domains to help us determine its shape. Okay? So molecular geometry is like its 3-dimensional shape. And so we're going to look at the number of electron domains. Okay? And I'm going to tell you what an electron domain is. Okay. An electron domain in very general terms is how many things, and I'm not going to say are bonded because that's a little bit different, how many things surround, that's a better word, surround the central atom. Okay? So within electron domains, we can have bonding domains and non-bonding domains. Okay, so there's a difference there. So that's why I said surround instead of how many things are bonded to, okay? So how many things surround the central atom? Okay, so just by looking at its molecular formula, it would be pretty near impossible to try to determine its 3-dimensional shape. So we're going to have a few different ways that we can utilize to determine its 3-dimensional shape, its molecular geometry. Okay, oops, sorry. I'll let you finish. That last bullet is just kind of for your information. You don't have to have that down in your notes necessarily. But most of the time, it's hard for you to look at a formula, right, H2O, and automatically know, oh yeah, that's going to be bent, right, or that's going to be tetrahedral, or whatever it is. It's going to be hard for you to look at its formula only and determine its shape. So we have this a set of rules again to help us determine its molecular geometry. Okay, and this sets of rules is called, I call it Vesper theory. I know that's not really what the abbreviation is spelled like, but that's kind of what I call it. Okay, so Vesper theory, VSEPR. It stands for Valence-Shell, Electron-pair, Repulsion theory. Okay, so that term you need to be familiar with. And I'm going to break down kind of what that means here just a second. Okay, Valence-Shell, Electron-pair, Repulsion. Try to break that down into a little bit more plain terms. What do you think in general that means? What does Valence-Shell mean? The outermost, right? And those are the only electrons that bond, right? Inner shell electrons do not bond because it's full octets. Too much work, right? The only electrons that bond are the valence shell electrons, okay? So valence shell means we're talking about the outermost shell. Electron pair, what's that mean? How many? Right, 2. And pairs of electrons can come in what 2 forms? A bond or a lone pair, right? So we're talking about outer shell electrons that are either bonded or non-bonded, right? And then we talk about the term repulsion. What's repulsion mean? What'd you say? Yeah, pushing away, right? That you repel each other. Okay, so what this means is that you can write this down in a shortened version, that's fine, but this essential definition is repulsion between sets of valence electron causes these sets to be oriented as far apart as possible. Okay. So I put a little, kind of easier definition at the bottom. Electrons repel each other. They want to be as far apart as possible. Okay, and so we're talking about if an element has, I'm going to draw a really non-real Lewis structure here, but let's just say, I've got carbon dioxide, right? I've got carbon and 2 oxygens. Do you think these oxygens would like to be right next to each other like this? No, because the electrons in this bond don't want to be close to the electrons in that bond, right? They want to be all the way on the other side. Okay, so instead of having them right next to each other, right, how far away can two things possibly be in a straight, okay, in terms of an angle, how far away can two things possibly be? 180 degrees, right? There's 180 degrees between this set of electrons and this set of electrons. Okay, so when they orient themselves, they're going to orient themselves in a way that they're going to be as far apart as possible. Okay, if there were three things bonded to the central atom, how far away could they orient themselves, do you think? Right, into thirds. So out of 360 degrees, approximately how far away are each of those?
45.
More than that. Nope, more than that. 360 divided by 3 is 120. Okay? Okay, so this works, this method kind of works for things that are in one plane, right, that lay flat. Now we're going to start talking about things that are in 3 dimensions. So you will need that handout I gave you with the Pauling scale on one side. The other side is molecular geometry, which is what we're getting into. So we talked about this term electron domain. So electron domain is how many things are surrounded to the central atom or surrounded by the central atom. Okay, electron domains can be bonding or non-bonding. So it's as simple as a bonding domain contains a bond, right? One or more bonds. A non-bonding domain contains a lone pair. That's it. Okay? And this is important to reiterate, is that it contains a single lone pair. Okay, so it's not like if you've got some lone pairs, that's one non-bonding domain. That's not how it works, right? If you've got 2 lone pairs on your central atom, you've got 2 non-bonding domains. Okay? And I should point out here that we're looking at electron domains on the central atom only. Okay, we're looking at just the central atom here. Okay, so we're looking at how things stem from the central atom to give us our 3-dimensional shape. Okay, and you have to be able to tell, look at a Lewis structure and find out how many bonding domains and how many non-bonding domains, because that will be your clue as to its molecular geometry or its 3-dimensional shape. Okay. Water. Okay, this is the Lewis structure for water. So how many electron domains in total are on the central atom? 1, 2, 3, 4, right? 4 total domains. That's it. Okay? So a non-bonding domain contains a single lone pair, and a bonding domain contains a bond to one atom, right? It could be a double bond, could be a triple bond, but it's to that atom. Okay? We'll talk a little bit more about that in a little bit. So 4, how many of them are bonding domains?
2.
2 of them, and how many are non-bonding domains? 2. Okay? So based on what we know here, we've got 4 total domains. So I want you to look at your molecular geometry sheet. 4 total domains, right? Total electron domains goes down this side of the table. And how many lone pairs do we have? 2. So slide over to where it says 2 lone pairs, which means the molecular geometry for water is called bent. Right? You don't have to put quotations. Bent. Okay? So as you look on this molecular geometry sheet, I want you to notice a couple things. When you start getting into this 4 total domains, you start seeing how some of the bonds are drawn with dots and some of them are drawn with kind of a triangle type shape. Do you see what I'm talking about? Okay, those indicate to us 3 dimension. So a dotted line, a dotted bond, means that that element or that atom is really going backwards, kind of like into your sheet. And the one that's drawn into it with the triangle or the thicker black line is coming out. Okay, so if you look, let's say, at a trigonal pyramid, which is a 3 and 1, or a 4 and a 1 lone pair. Do we see where I'm at here? Trigonal pyramid. Okay, that means that the bottom of it forms this triangle, right? And we've got a true pyramid, right? We've got a triangle and then we've got a pyramid. So we've got things coming out at you, things going backward. So it's not just sitting in on one plane, right? It's 3-dimensional now. So that'll kind of show you on here how we draw that 2-dimensionally. Okay, we're going to look at some of this a little bit more in depth with a computer app, so you'll be able to look at the molecule, move it around so you can really see what's going on. But on your sheet, that's what those extra lines or those different lines mean. Dotted line means it's kind of going backwards into the page. Thicker line means it's coming out at you a little bit. Okay, but water is in one plane, right? So it just doesn't have anything else crazy going on. All right, let's try Lewis structure for BCl3. Give me the Lewis structure for BCl3. Okay, would you agree here with our Lewis structure? Okay, so once we start finding molecular geometry, that's going to be our goal here, is what's our molecular geometry now of boron trichloride. We're going to look at electron domains. So how many electron domains do we have?
3.
3. 1, 2, 3. And how many lone pairs? None. So that means our shape is trigonal planar. Okay? Trigonal planar. Would you agree? Yeah.
When do you know to put like a double bond on the, because you only have 6 of those.
Okay, so boron is one of those that's going to be okay having an incomplete octet. Okay, so here, instead of making chloride uncomfortable and putting a double bond and 2 pairs, right, if we leave it by where it's at right now, chlorine is happy with 3 pairs and 1 bond, which is what it wants to have. Okay? You got to know that boron is most of the time okay. That's the one exception that's okay. And then third row or below are okay having expanded. That's just how it goes. Okay? Yeah, it's a little bit tricky. Yeah, most of the time boron is just going to have 3. Good. Tetrahedral. Tetrahedral. CBr4. So we had carbon bonded to all 4 things, which would give us a tetrahedral geometry. Okay. All right. I'm going to work through this just a little bit quicker. Let's try NH3.
So does that mean that you have to put it like that?
You don't have to draw it like that now.
Oh.
Try NH3. So how many total domains do we see on NH3? How many total?
4.
Total is 4. 1, 2, 3, 4. So you follow 4. And then we have how many lone pairs? 1. So it should be trigonal pyramid. Trigonal pyramid. 4 total domains. 1, 2, 3, 4. right? We follow it down to 4, and then we say there's one lone pair, so we go over. Okay? So essentially what this is shaped like is a real pyramid, right? Okay, a pyramid shape, not a real pyramid. A triangle that comes up to a pyramid, okay? Because a real pyramid, I think, has 4 things on the bottom. Okay, so a triangle that comes up to a pyramid. So we're going to look at that in 3-dimension next class a little bit more closely. The last thing that I wanted to touch on is that if we have a double bond, okay, so if we have a double bond, they count only as one domain. Okay, so if I had a carbon bonded to an oxygen as part of a molecule, right, let's say I got other things going on with carbon over here. Okay, so if I had carbon that had a bond, it looks like this. This domain with a double bond still only counts as one bonding domain. Okay, the same would be true if a triple bond was found there, right? So here we've got 1, 2, 3 bonding domains with no lone pairs. So in this example, it would be trigonal planar. Okay. Are we on the same page with that?
Yeah.
Okay. So